time passes. You feel it in every breath, in the rhythm of your heartbeat, in the way shadows lengthen across a room as the sun moves through the sky. It is perhaps the most immediate and inescapable aspect of existence, yet it is also one of the most mysterious. Physics tells us that time is not what it seems, not an absolute backdrop against which events unfold, but something far stranger, a dimension interwoven with space, warped by mass and energy, and possibly without the privileged direction we call forward. A clock measures time by counting regular intervals. The swing of a pendulum, the vibration of a quartz crystal, the oscillation of cesium atoms, all provide a repeating rhythm that can be divided into seconds, minutes, hours. 1 second is currently defined as the duration of 9,192,631,770 oscillations of the radiation, corresponding to the transition between two energy levels of the cesium-133 atom. This definition is precise and reproducible, the same in every laboratory on Earth, and, as far as we can tell, everywhere in the universe. Yet the intervals measured by identical clocks can differ depending on their motion and location, a consequence of relativity. Special relativity, formulated by Einstein in 1905, revealed that time is relative to the observer. If you could board a spacecraft and travel at a significant fraction of the speed of light, time would pass more slowly for you than for someone who remained on Earth. This is not an illusion or a trick of perception, but a fundamental property of space-time. The faster you move through space, the slower you move through time, in such a way that the speed of a light remains constant for all observers. If you travelled to a distant star and returned, you would have aged less than those who stayed behind. A prediction confirmed by experiments with atomic clocks flown on airplanes and satellites. This slowing of time, called time dilation, arises from the geometry of space-time. Space and time are not separate entities, but components of a four-dimensional continuum. Events are located not just by where they occur, but also by when. And the interval between two events, the space-time distance, is invariant. The same for all observers, even though the separate measurements of space and time vary. The mathematics of this is captured in the Minkowski metric, which defines distances in space-time by combining spatial separations and temporal separations, with a minus sign that distinguishes time from space. The speed of light, approximately 299,792,458 meters per second, is not just the speed at which light travels, but a fundamental speed limit built into the structure of space-time. Nothing with mass can reach this speed because doing so would require infinite energy. Photons, which have no mass, always travel at this speed and, from their own perspective, experience no passage of time at all. A photon emitted by a distant galaxy billions of years ago from its own frame of reference arrives at your eye instantaneously, even though from your perspective it has been travelling for eons. General relativity, published by Einstein in 1915, extended these ideas to include gravity. It showed that massive objects warp the fabric of space-time, and this curvature affects the flow of time. Clocks run slower in stronger gravitational fields, a phenomenon that must be accounted for in technologies like GPS. Satellites orbit Earth at high altitudes where gravity is weaker, and their clocks tick faster than clocks on the surface by about 45 microseconds per day. At the same time, their motion causes time dilation that slows their clocks by about 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground-based clocks. Without correcting for these relativistic effects, GPS position errors would accumulate at a rate of about 10 kilometers per day. Near a black hole, time dilation becomes extreme. At the event horizon, time slows to a standstill relative to a distant observer. An astronaut falling into a black hole would, from their own perspective, cross the horizon in a finite amount of proper time. But to an outside observer, they would appear to slow down, their image freezing at the horizon, and fading as light becomes increasingly redshifted. Time, near such an object, becomes almost unrecognizable compared to our everyday experience. Yet despite these relativistic effects, we perceive time as flowing in one direction, from past to future. We remember yesterday, but not tomorrow. Eggs break, but do not spontaneously reassemble. Heat disperses, but does not concentrate. This asymmetry is not explained by the fundamental laws of physics, most of which are time-symmetric. If you filmed particles colliding at the microscopic level and played the video backward, the reversed motion would still obey the laws of mechanics. The arrow of time, it turns out, is not inscribed in the equations of motion, but emerges from the second law of thermodynamics. Entropy, a measure of disorder, tends to increase in isolated systems. This is a statistical statement. There are vastly more disordered configurations than ordered ones, so a system left to itself will almost certainly evolve toward higher entropy. The universe, as a whole, began in a state of extraordinarily low entropy, hot, dense, and smooth immediately after the Big Bang. As it expanded and cooled, matter clumped together under gravity, forming stars and galaxies, but the overall entropy continued to increase. The second law does not forbid local decreases in entropy, such as the formation of a snowflake or the growth of a tree, but these always occur at the expense of greater increases elsewhere. The directionality of time, then, is linked to the initial conditions of the universe. If the Big Bang had started with maximum entropy, there would be no preferred direction of time, no past or future, only a featureless equilibrium. But it did not. The universe began in a highly ordered state, and the arrow of time points in the direction of increasing entropy. This is why we remember the past and not the future. Memories are low-entropy configurations encoded in the structure of our brains, and they form as entropy increases in our surroundings. Time's flow is also connected to causality. The principle that causes precede their effects. When you flip a light switch, the electrical current flows, and the bulb illuminates. The flipping causes the illumination, not the other way around. This temporal ordering is preserved by the speed of light limit. Events can only influence each other if a signal travelling at or below the speed of light can connect them. This defines a light cone, a region of space-time containing all events that can be reached from a given point by travelling at or below light speed. Events outside your past light cone cannot have influenced you. Events outside your future light cone cannot be influenced by you. Causality is built into the geometry of space-time. Some theories in physics suggest that time might not be fundamental but emergent, a macroscopic phenomenon arising from more basic timeless laws. In quantum mechanics, the Schrödinger equation describes how quantum states evolve, and this evolution is inherently time-dependent. But in attempts to unify quantum mechanics with general relativity, such as in quantum gravity, time loses its privileged status. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, contains no time variable at all. How time emerges from such a timeless framework remains one of the deepest unsolved problems in theoretical physics. On human scales, time is measured by biological rhythms. The circadian clock in your brain synchronizes physiological processes to the 24-hour cycle of day and night. Even isolated from external cues, the body maintains an internal rhythm close to, but not exactly 24 hours. This internal clock is reset daily by light entering the eyes and signalling to the suprachiasmatic nucleus, a small cluster of neurons in the hypothalamus. Disruptions to this rhythm, shift work, jet lag, exposure to artificial light at night, can impair sleep, mood, and metabolic function. Evidence that our biology is deeply attuned to the passage of time. Time is also perceived subjectively. A minute can feel like an eternity or pass in an instant, depending on context. As we age, time seems to accelerate, a phenomenon likely related to the way memory encodes novel experiences. Childhood is rich with new experiences, each forming distinct memories, So in retrospect, it seems to span a long time. Adulthood, especially when routine dominates, produces fewer memorable events, and years seem to blur together. The subjective experience of time, shaped by attention, emotion, and memory, does not always align with the ticking of a clock. The nature of time has occupied philosophers and scientists for millennia. Is time real, or is it an illusion of consciousness? Does the future already exist, laid out in space-time like a landscape, or does it come into being moment by moment? These questions remain unresolved, but physics provides a framework for thinking about them. Time is a coordinate, a dimension, a parameter in equations, and a direction defined by entropy. It is both deeply strange and utterly familiar, a mystery woven into the fabric of existence. Understanding time does not rob it of meaning. Knowing that time dilation is real does not make your experience of time less immediate. Recognizing that the arrow of time is statistical does not make the past less fixed or the future less open. If anything, these insights deepen the sense of wonder, revealing that time, like space and matter, is part of the universe's structure, shaped by the same laws that govern stars and atoms, and yet intimately connected to the flow of your thoughts, the beating of your heart, and the unfolding story of your life. The universe had a beginning. This was not always accepted. For much of human history, many believed the cosmos to be eternal, unchanging in its essentials even if details varied. But in the 20th century, observations and theory converged on a remarkable conclusion. The universe is expanding, and if you run the expansion backward in time, all matter and energy converge to a single point of infinite density and temperature. This moment, roughly 13.8 billion years ago, is what we call the Big Bang. The evidence for the Big Bang comes from multiple sources. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This relationship, now known as Hubble's law, implies that space itself is expanding. Galaxies are not moving through space away from us. Space is stretching, carrying galaxies along with it. If the universe is expanding now, it must have been smaller and denser in the past. The cosmic microwave background radiation provides further confirmation. In 1965, Arno Penzias and Robert Wilson detected a faint glow of microwave radiation coming from all directions in the sky. This radiation is the cooled remnant of the intense heat that filled the universe when it was only 380,000 years old. At that time, the universe had cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. Before this recombination, photons were constantly scattered by free electrons, making the universe opaque. After recombination, photons could travel freely, and the universe became transparent. The light from that moment has been travelling through space ever since, stretched to longer wavelengths by the expansion of the universe, now observed as microwave radiation, with a temperature of about 2.7 Kelvin. The Big Bang was not an explosion in space, but an expansion of space. There was no centre, no edge, no outside. Every point in the universe was once in the same place, and as space expanded, distances between points increased. This expansion continues today, and it is accelerating, driven by a mysterious component called dark energy, which exerts a kind of negative pressure, pushing space apart. In the first moments after the Big Bang, the universe was unimaginably hot and dense. At 10 to the minus 43 seconds, the Planck time, the smallest interval of time that has physical meaning in current theories, the temperature was around 10 to the 32nd Kelvin, and the four fundamental forces may have been unified into a single force. As the universe expanded and cooled, these forces separated. Gravity split off first, then the strong nuclear force, and finally the electromagnetic and weak nuclear forces separated at around 10 to the minus 12 seconds, when the temperature dropped to about 10 to the 15th power Kelvin. During the first few minutes, nuclear fusion occurred in the hot, dense plasma, forming the lightest elements. Protons and neutrons combined to form deuterium, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, lasted only about 20 minutes, ending when the universe cooled below the temperature required for fusion. The predicted abundances of these light elements match observations with remarkable precision, providing strong evidence for the Big Bang model. For the next 380,000 years, the universe was filled with a hot plasma of protons, electrons, and photons, opaque to light. Then came recombination, the formation of neutral atoms, and the release of the cosmic microwave background. The universe entered what is sometimes called the Dark Ages, a period when no stars yet existed, and the only light was the fading glow of the Big Bang, redshifting into the infrared. Gravity, acting on tiny density fluctuations imprinted during inflation, a brief period of exponential expansion in the universe's first fraction of a second, began to pull matter together. Regions slightly denser than average attracted more matter, growing denser still, while less dense regions became voids. The first stars formed around 100 to 200 million years after the Big Bang, igniting when collapsing clouds of hydrogen and helium became hot and dense enough for nuclear fusion. These first stars, called Population 3 stars, contained no heavy elements, only hydrogen and helium. They were likely much more massive than typical stars today and burned intensely, exhausting their fuel in just a few million years before exploding as supernovae, enriching the surrounding gas with heavier elements. Galaxies formed from the gravitational collapse of large regions of dark matter and ordinary matter. Dark matter, which does not interact with light, provided the gravitational scaffolding around which galaxies assembled. Ordinary matter, gas, fell into these dark matter halos, cooled, and formed stars. Over billions of years, galaxies merged and evolved, growing in size and complexity. The Milky Way, our home galaxy, formed around 13 billion years ago, and has since merged with dozens of smaller galaxies. It contains roughly 200 to 400 billion stars, along with vast clouds of gas and dust, all orbiting a supermassive black hole at the galactic centre, with a mass of about 4 million times that of the Sun. The Solar System formed 4.6 billion years ago from a rotating cloud of gas and dust, the Solar Nebula, left over from earlier generations of stars. Most of the mass collapsed into the centre, forming the Sun. The remaining material flattened into a disk, within which dust grains collided and stuck together, forming larger and larger bodies. Planetesimals, kilometre-sized objects, grew through accretion, sweeping up nearby material. Some became planets, others collided and merged. The inner solar system, closer to the Sun, was too hot for volatile substances like water and methane to condense, so the terrestrial planets, Mercury, Venus, Earth, and Mars, formed from rock and metal. In the outer solar system, beyond the frost line, ice could condense, allowing the gas giants, Jupiter, Saturn, Uranus, and Neptune, to grow massive cores that then captured thick atmospheres of hydrogen and helium. Earth underwent a violent early history. Its surface was molten, bombarded by asteroids and comets, and the atmosphere was likely composed of carbon dioxide, nitrogen, water vapour, and trace amounts of other gases. The Moon formed from debris ejected by a giant impact, and its gravitational influence stabilised Earth's axial tilt, contributing to a more stable climate. By 4 billion years ago, the surface had cooled enough for liquid water to exist, and the stage was set for the emergence of life. Time, in the context of cosmology, is measured by the expansion of the universe. The age of the universe is determined by running the expansion backward to the point where all distances go to zero, the Big Bang. This age, about 13.8 billion years, is inferred from measurements of the Hubble constant, which quantifies the rate of expansion and from observations of the cosmic microwave background, which reveal the conditions in the early universe. These measurements are consistent with each other and with the observed ages of the oldest stars, which are around 13 billion years old. The expansion of the universe does not have a centre or an edge in ordinary three-dimensional space. It is the space itself that expands, stretching the distances between galaxies. An analogy often used is the surface of an inflating balloon. As the balloon expands, dots drawn on its surface move apart, not because they are moving across the surface, but because the surface itself is stretching. Similarly, galaxies recede from one another because the space between them is expanding. An observer in any galaxy would see all other galaxies moving away, with more distant galaxies receding faster. The ultimate fate of the universe depends on its composition and the nature of dark energy. Current observations suggest that the universe will continue expanding forever, driven by dark energy. As it does, galaxies will move farther apart, stars will exhaust their fuel and die, and eventually, after trillions of years, the universe will become cold and dark, a state sometimes called the heat death, in which entropy has reached its maximum and no further work can be extracted. This is far in the future, but it is the direction in which the arrow of time points. Yet within this vast sweep of cosmic history, there are islands of order, stars, planets, living organisms. These structures form and persist because the universe is not yet at maximum entropy. Energy flows from hot regions to cold ones, and in the process, it can be harnessed to build and maintain complex systems. Life is one such system, a temporary eddy in the river of entropy, sustained by the energy of the sun, which itself draws energy from nuclear fusion, burning hydrogen into helium and radiating the difference into space. Time, at the cosmic scale, is not uniform. Different parts of the universe, depending on their density and motion, experience time at different rates. Near the supermassive black hole at the centre of the Milky Way, time runs slower than it does here on Earth. In the vast voids between galaxy clusters, where matter is sparse, time flows slightly faster. These differences are small but measurable, a testament to the relativity of time and its deep connection to the structure of space-time. The history of the universe is also the history of time itself. Before the Big Bang, there may have been no time, at least not in a form we can describe with current physics. Time as we know it began with the expansion of space, and it will continue as long as the universe expands. Whether time is infinite or finite, whether it had a beginning or will have an end, are questions that push the boundaries of science and philosophy. But within the span of cosmic history we can observe and measure. Time provides the framework within which all events unfold. The dimension along which causes precede effects, entropy increases, and the universe evolves from simplicity toward complexity, and eventually back toward uniformity. Time travel is a staple of science fiction, but physics suggests that under certain conditions it might not be entirely impossible. The equations of general relativity permit solutions in which closed time-like curves exist, paths through space-time that loop back on themselves, allowing a traveller to return to their own past. These are not mere mathematical curiosities. They arise in specific space-time geometries, such as those involving rotating black holes or traversable wormholes. A rotating black hole, described by the Kerr metric, has two event horizons and a region called the ergosphere, where space-time is dragged along with the rotation. In principle, an object entering the ergosphere could extract energy from the black hole's rotation and escape, a process called the Penrose process. Deep within the inner horizon, the structure of space-time becomes so warped that trajectories can curve back in time. However, the interior of such a black hole is likely unstable, with intense tidal forces and radiation that would destroy any traveller. Whether these regions truly permit time travel, or whether some unknown law of physics prevents it, remains uncertain. Wormholes, hypothetical tunnels connecting distant points in space-time, offer another speculative route. If a wormhole could be created and stabilized, a task requiring exotic matter with negative energy density, something not known to exist in sufficient quantities, it might serve as a shortcut through space. If one end of the wormhole were accelerated to near the speed of light and then returned, time dilation would cause the two ends to be at different times, potentially allowing travel to the past. The problem is that such a configuration might become unstable, collapsing or producing a singularity before any signal could travel through. Causality poses a significant obstacle. If you could travel back in time and prevent your own departure, a paradox arises. One resolution, proposed by some physicists, is the Novikov self-consistency principle, which suggests that any action taken by a time traveller must be consistent with the history that has already occurred. Events would conspire to prevent paradoxes, not through some mysterious force, but as a constraint imposed by the structure of space-time itself. Another possibility, explored in the many worlds interpretation of quantum mechanics, is that travelling to the past creates a branching timeline, so that changes occur in a parallel universe rather than altering the traveller's original past. Forward time travel, on the other hand, is straightforward and confirmed by experiment. If you travel at high speed, or reside in a weaker gravitational field, you will age more slowly relative to others. Astronauts on the International Space Station, orbiting at about 28,000 km per hour, experience time dilation and age slightly less than people on Earth, about 0.01 seconds less per year. If you could travel near the speed of light, the effect would be dramatic. A journey to a star 10 light-years away at 99%, the speed of light would take about 10 years from Earth's perspective. But the traveller would experience only about 1.5 years due to time dilation. Upon return, 20 years would have passed on Earth, while the traveller aged only 3 years. This is time travel to the future, and it is permitted by the laws of physics. The question of whether backward time travel is possible remains open. Some physicists argue that quantum effect or other unknown principles will prevent closed time-like curves from forming. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent time machines, preserving causality. Others, like Kip Thorne, have shown that general relativity does not forbid them, and it remains unclear whether a complete theory of quantum gravity will close the loophole or reveal new possibilities. Time, in quantum mechanics, takes on additional subtleties. The Schrödinger equation, which governs the evolution of quantum systems, treats time as a parameter, external to the system, not subject to quantum uncertainty. Position and momentum are quantum observables, represented by operators that do not commute, leading to the uncertainty principle. But time is not an operator in standard quantum mechanics. It is a classical background against which quantum events unfold. This asymmetry between time and space becomes problematic when attempting to unify quantum mechanics with general relativity, where time is a coordinate on equal footing with space. In quantum field theory, the framework that combines quantum mechanics with special relativity, particles are excitations of underlying fields that permeate space-time. The vacuum is not empty, but seethes with virtual particles, particle-antiparticle pairs that spontaneously appear and annihilate on timescales so short they cannot be directly observed. These virtual particles have measurable effects, such as the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force due to the suppression of certain vacuum fluctuations between them. Time symmetry, or the lack thereof, appears in subtle ways at the quantum level. Most fundamental interactions are symmetric under time reversal. If you reverse the direction of time, the laws of physics remain the same. But the weak nuclear force exhibits a slight violation of this symmetry, a phenomenon observed in the decay of certain subatomic particles called kaons. This violation is related to the CP symmetry, the combined symmetry of charge conjugation and parity, and suggests that the universe distinguishes between past and future at a fundamental level, albeit weakly. The measurement problem in quantum mechanics also involves time. Before measurement, a quantum system exists in a superposition of states, described by a wave function that evolves deterministically according to the Schrödinger equation. Upon measurement, the wave function collapses to a definite outcome, a process that appears to be instantaneous and non-deterministic. The exact mechanism of wave function collapse, and whether it is a physical process or merely a change in information, remains one of the central puzzles of quantum mechanics. Some interpretations, such as the many worlds interpretation, avoid collapse by proposing that all possible outcomes occur, each in a separate branch of reality. Time's role in entropy and thermodynamics extends into the quantum realm. The second law of thermodynamics, which states that entropy tends to increase, emerges from the statistical behavior of large numbers of particles. In small quantum systems, entropy can fluctuate, and temporary decreases are possible. But as systems grow larger, the statistical tendency toward higher entropy becomes overwhelming. Quantum mechanics introduces additional subtleties, such as entanglement entropy, which measures the amount of quantum correlation between parts of a system. This entropy can increase even when the system is isolated, reflecting the spread of quantum information rather than classical disorder. Black holes provide a testing ground for the interplay of quantum mechanics, gravity, and thermodynamics. Jacob Bekenstein proposed in the 1970s that black holes have entropy proportional to the area of their event horizons, not their volume. This was confirmed by Hawking's discovery that black holes emit radiation and have a temperature. A black hole's entropy is enormous, far larger than any ordinary object of comparable mass, and this entropy increases when matter falls in. But Hawking radiation causes black holes to lose mass and eventually evaporate, raising the question, what happens to the information that fell into the black hole? If it is destroyed, quantum mechanics is violated. If it escapes in the radiation, how does it do so without violating the no-hair theorem, which states that black holes have no structure other than mass, charge, and spin? This is the black hole information paradox, and it has motivated much recent work in theoretical physics. Some proposed solutions involve subtle correlations encoded in the Hawking radiation, while others suggest that information is stored on the event horizon itself in a holographic manner. The holographic principle, inspired by these considerations, proposes that all the information contained in a volume of space can be encoded on its boundary, much as a two-dimensional hologram can encode a three-dimensional image. This idea has profound implications for quantum gravity and the nature of space-time. Time, then, is not a simple backdrop but an active participant in the dynamics of the universe. It is entangled with space, warped by mass and energy, quantized at the smallest scales, and directional due to entropy. Its passage is relative, dependent on motion and gravity, and yet it provides the structure within which causality operates and events unfold. Whether time is fundamental or emergent, continuous or discrete, finite or infinite, these remain open questions at the frontier of physics and philosophy. Our experience of time is shaped by biology and psychology, but it rests on a foundation of physical law. The circadian rhythms that govern sleep and wakefulness, the neural processes that create the sensation of the present moment, the memory systems that distinguish past from future, all are embedded in a universe where time is a dimension, a direction, and a mystery still not fully understood. The present moment feels unique. Right now, this instant is when experience happens, when decisions are made, when the future becomes the past. Yet physics offers no special status to now. The equations of motion, whether Newtonian mechanics or general relativity, treat all moments equally. Time is a coordinate, and any point along it can be chosen as a reference. The sensation that time flows, that there is a moving present dividing past from future, appears nowhere in the mathematical description of the universe. This creates a puzzle. If the laws of physics do not distinguish between different moments in time, Why do we experience time as flowing? One answer comes from the way we interact with the world. Our brains construct a narrative from sensory input, memory, and prediction, creating the illusion of a continuous present. Neurons take time to fire, signals take time to propagate, and the brain integrates information over intervals of a few hundred milliseconds. What we perceive as now is actually a synthesis of recent past and anticipated future, smoothed into a coherent experience. The brain timestamps events, but not always accurately. Experiments show that the perceived order of events can differ from their actual order. If you press a button and see a light flash, your brain registers the two as simultaneous, even though the neural processing of the visual signal takes longer than that of the tactile signal. The brain compensates, aligning the timestamps to create a coherent sense of causality. This temporal binding is essential for coordinated action. Catching a ball, playing music, speaking, all require precise timing, and the brain continually calibrates its internal clock based on sensory feedback. Attention influences the perception of time. When you're engaged and focused, time seems to pass quickly. When you're bored or waiting, it drags. This is not merely subjective distortion, but reflects differences in how the brain processes information. Novel, complex experiences demand more neural resources and produce richer memories, which in retrospect make a period seem longer. Routine, repetitive experiences are processed efficiently and leave fewer memory traces, compressing the subjective duration. Emotions also affect temporal perception. Fear can slow down subjective time, a phenomenon sometimes called bullet time, where events seem to unfold in slow motion during high-stress situations. This may result from increased attention and heightened memory encoding, so that more details are recorded, creating the impression of extended duration when recalled. Conversely, positive emotions and flow states, where a person is fully immersed in an activity, can cause time to seem to fly. The passage of time is central to memory. Episodic memory, the recollection of specific events, is organized temporally. You remember what happened earlier and what came later, constructing a personal timeline. The hippocampus plays a critical role in encoding these temporal sequences, and damage to this region disrupts the ability to form new time-ordered memories. Patients with hippocampal damage can recall events from before the injury, but cannot create new episodic memories, leaving them perpetually in the present, unable to track the passage of time through new experiences. Time cells discovered in the hippocampus fire in sequence during specific intervals, providing a neural mechanism for tracking time within events. These cells activate one after another as an experience unfolds, much like frames in a film, allowing the brain to encode not just what happened, but when it happened relative to other events. This temporal coding is flexible, adjusting to the duration of the interval being tracked, and it appears to be a fundamental component of how the brain represents time. The concept of simultaneity, seemingly straightforward, becomes problematic in relativity. Two events that appear simultaneous to one observer may not be simultaneous to another, moving at a different velocity. There is no universal now shared by all observers. Each observer has their own definition of simultaneity, determined by their motion through space-time. This relativity of simultaneity implies that the division of space-time into past, present, and future is observer-dependent. Events that are in your future might, from another reference frame, already exist in someone else's present. This leads to the block universe view, in which past, present, and future all exist equally, laid out in four-dimensional space-time like frames in a film strip. From this perspective, time does not flow. We simply traverse it, perceiving one moment after another as our consciousness moves along our world line. The entire history of the universe, from the Big Bang to its ultimate fate, is already determined, woven into the fabric of space-time. This view is consistent with general relativity but challenges our intuitive sense of free will and the openness of the future. Others argue for a growing block universe, in which the past and present exist, but the future does not yet. It comes into being as time progresses. This view attempts to reconcile the relativity of time with the intuition that the future is genuinely open, not yet fixed. However, it faces difficulties in defining a universal present, given the relativity of simultaneity. Presentism holds that only the present exists, the past is gone, and the future has not yet come into being. This aligns with subjective experience but is difficult to reconcile with relativity, which treats time as a dimension on par with space. If only the present exists, whose present? Observers in relative motion disagree about which events are simultaneous, so there is no single, objective present moment. The nature of time consciousness has been explored by philosophers as well as scientists. Edmund Husserl described temporal experiences involving retention, the immediate past that is still present in awareness, primal impression, the immediate now, and pretension, the anticipation of the immediate future. This structure allows us to perceive events as extended in time rather than as discrete, disconnected instants. When you listen to a melody, you do not hear isolated notes but a sequence unfolding, with each note retained in memory even as the next sounds. The sense of duration is distinct from the perception of succession. You can judge whether one interval is longer than another, and the brain uses multiple cues for this: physiological rhythms, the number of events within the interval, the cognitive load required to process them. Drugs that alter brain chemistry can distort time perception. Stimulants like caffeine and amphetamines can make time seem to pass more slowly by speeding up internal processes, while depressants like alcohol can have the opposite effect. Sleep further complicates our relationship with time. During sleep, consciousness is reduced, and the sense of time's passage is largely absent. When you wake, hours may have passed, but subjectively it feels instantaneous. REM sleep, the stage associated with vivid dreams, involves a different kind of temporal experience. Dreams can feel like they last for hours, though they typically occur in bursts of 10 to 20 minutes. The narrative structure of dreams creates a sense of duration, but the actual neural activity generating them is compressed in time. Aging changes the perception of time. Children experience time as passing more slowly, possibly because each year represents a larger fraction of their total life, or because childhood is filled with novel experiences that form distinct memories. As people age, routines become more common, and time seems to accelerate. The monotony of repetition compresses subjective time, while novelty expands it. This is why vacations or significant life events often seem longer in retrospect than mundane periods of equal duration. Cultural factors also shape temporal perception. Some cultures emphasize punctuality and schedules, treating time as a commodity to be managed. Others adopt a more flexible approach, where time is event-based rather than clock-based. These differences reflect varying priorities and social structures, but they rest on the same underlying biology: the circadian rhythms, neural processing, and memory systems that all humans share. The arrow of time, discussed earlier in terms of entropy, also manifests psychologically. We remember the past but not the future. We can influence the future but not the past. This asymmetry is so deeply ingrained that its absence would be unthinkable. Yet the microscopic laws of physics do not enforce this directionality. It emerges from initial conditions, the low entropy state of the early universe, and from the statistical behavior of large systems. Our memories are physical records, low entropy structures encoding information about past states, and they form because entropy increases in the process of recording. The flow of time, then, may be less a feature of the external world and more a feature of how conscious systems like ourselves interact with that world. We are thermodynamic beings, processing information, forming memories, and making predictions, all of which require distinguishing past from future. Time, as we experience it, is the dimension along which causes led to effects, along which we age, along which stories unfold. It is both the stage on which existence plays out and an emergent property of our engagement with the universe. Clocks are everywhere. Your heart beats roughly once per second at rest. The Earth rotates once every 24 hours. The Moon orbits Earth in about 27.3 days. Earth orbits the Sun in 365.25 days. These natural cycles have served as timekeepers for millennia, and they are products of fundamental physics: gravity, rotation, orbital mechanics. But the most precise clocks we have built do not rely on celestial mechanics. They rely on the quantum behavior of atoms. An atomic clock measures time by counting the oscillations of electromagnetic radiation emitted or absorbed by atoms transitioning between energy levels. The cesium-133 atom, used in the international definition of the second, has a hyperfine transition, a small energy difference caused by the interaction between the nucleus and the surrounding electron, that corresponds to microwave radiation with a frequency of exactly 9,192,631,770 Hz. This frequency is extraordinarily stable, varying by less than 1 part in 10 to the 14th power, which means a cesium clock would lose or gain less than 1 second in 100 million years. More advanced atomic clocks use optical transitions, higher frequency transitions in atoms like strontium or ytterbium, which oscillate at hundreds of terahertz. These optical lattice clocks are even more precise, accurate to 1 part in 10 to the 18th power. Such a clock would neither gain nor lose a second over the age of the universe. At this level of precision, relativistic effects become measurable over centimetre scale height differences. Moving a clock just 2 centimetres higher in Earth's gravitational field causes it to tick slightly faster, a difference that can be detected with current technology. These clocks have practical applications beyond timekeeping. They enable tests of fundamental physics, searching for variations in fundamental constants or deviations from general relativity. They improve GPS and other navigation systems which rely on precise synchronization. They may one day enable gravitational wave detection through timing arrays, networks of clocks sensitive enough to detect the stretching and compressing of space-time as gravitational waves pass by. The precision of atomic clocks also reveals the limits of defining time itself. As clocks become more accurate, the question arises, what is time exactly that we are measuring? In classical physics, time is a parameter, an independent variable, external to the system. In relativity, time is a coordinate, intertwined with space. In quantum mechanics, time is a background against which wave functions evolve. But in quantum gravity, time may lose even this status, becoming an emergent property of a more fundamental timeless description. Some approaches to quantum gravity suggest that space-time itself is quantized, made of discrete units at the Planck scale, about 10 to the negative 35th meters and 10 to the negative 43rd seconds. At this scale, the smooth continuum of space-time breaks down, and concepts like distance and duration may no longer have clear meaning. Loop quantum gravity, for instance, proposes that space-time is woven from loops of gravitational field lines, and time emerges from the way these loops interact and change. String theory, another approach to quantum gravity, describes particles as tiny vibrating strings, and the different modes of vibration correspond to different particles. Time, in this framework, is still a coordinate, but the theory requires extra dimensions, 10 or 11 in total depending on the version, most of which are compactified, curled up at scales too small to observe directly. Whether time itself could be compactified or emergent in some configurations remains an open question. The problem of time in quantum gravity is profound. In general relativity, the dynamical equations describe how space-time curvature evolves in time. But when quantized, the resulting Wheeler-DeWitt equation has no explicit time variable. It describes the quantum state of the entire universe as static, timeless. How then does change occur? How do we recover the experience of time passing, of events unfolding in sequence? One proposal is that time is a relational concept. defined by the correlations between different parts of the universe. A clock does not measure time in an absolute sense, but rather its change relative to other systems. In this view, time is not fundamental but emergent from the dynamics of matter and fields. The universe as a whole may be timeless, but subsystems within it experience time as they evolve relative to one another. Another idea, called the thermal time hypothesis, suggests that time is related to thermodynamics. The flow of time emerges from the increase of entropy, and what we perceive as time's passage is the statistical tendency for systems to evolve toward higher entropy states. This connects the arrow of time to the second law of thermodynamics and grounds temporal experience in the physical processes of dissipation and irreversibility. Time may also be fundamentally statistical. In a universe described by quantum mechanics, outcomes are probabilistic, and the passage of time might be understood as the process by which probabilities are realized, the collapse of the wave function, or the branching of the many worlds tree. Each moment brings a selection from the superposition of possibilities, and the sequence of these selections defines the flow of time. Synchronization is another subtle aspect of time. Events separated by space can be synchronized using light signals, but this synchronization is convention-dependent in relativity. Einstein's convention is to define simultaneity such that light travels at the same speed in all directions, but other conventions are possible. Distant clocks can be synchronized by exchanging signals, but the result depends on the assumptions made about the signal's travel time. There is no absolute synchronization, only agreement within a chosen reference frame. Biological clocks, though less precise than atomic clocks, are remarkably robust. The circadian rhythm persists even in constant darkness, driven by molecular feedback loops within cells. The proteins clock and BMAL1 activate genes that produce proteins PER and CRY, which accumulate, eventually inhibiting clock and BMAL1, causing their own production to cease. As PER and CRY degrade, the cycle begins again, taking about 24 hours. This molecular oscillator is present in nearly every cell, synchronized across the body by signals from the suprachiasmatic nucleus in the brain. Plants too have circadian rhythms, regulating photosynthesis, growth and flowering. Cyanobacteria, among the simplest organisms, possess circadian clocks, suggesting that timekeeping is ancient and fundamental to life. These biological clocks allow organisms to anticipate daily changes, dawn, dusk, temperature shifts, and coordinate internal processes accordingly. The fitness advantage of such anticipation is clear. Being prepared for predictable changes improves survival and reproduction. Jet lag and shift work disrupt the alignment between internal and external time, leading to sleep disturbances, impaired cognition, and metabolic issues. The circadian system takes days to adjust to a new time zone, and chronic misalignment as experienced by shift workers is associated with increased risk of cardiovascular disease, diabetes, and certain cancers. This reflects the deep integration of circadian rhythms with metabolism, immune function, and cellular repair. Chronobiology, the study of biological rhythms, has revealed that many physiological processes vary predictably over the day. Body temperature peaks in the late afternoon and reaches its lowest point in the early morning. Hormone levels fluctuate. Cortisol rises before waking. Melatonin increases in the evening. Cognitive performance varies, with alertness and reaction timed typically best in the mid-morning and early evening. Even the effectiveness of medications can depend on the time of administration, a field called chronopharmacology. The alignment of biological and astronomical time is not perfect. The human circadian period, measured in the absence of external cues, averages slightly longer than 24 hours, about 24.2 hours for most people. Daily exposure to light resets the clock, synchronizing it with the Earth's rotation. Before artificial lighting, this synchronization was strong and consistent. with dawn and dusk providing clear signals. Modern life, with its electric lights and screens, weakens these signals, allowing the circadian clock to drift, contributing to sleep disorders and reduced well-being. Time at all scales is measured by change. A clock counts cycles. A radioactive isotope decays, its half-life providing a measure of elapsed time. The expansion of the universe stretches wavelengths, redshifting light and providing a cosmic clock. Biological aging is marked by cellular changes, telomere shortening, accumulation of DNA damage, decline in regenerative capacity. Geological time is recorded in rock layers, fossil sequences, and isotopic ratios. Each of these processes provides a way to mark time's passage, and together they form a coherent picture of a universe evolving from past to future. Yet the question remains, is time real, or is it a construct? Does it flow, or do we simply move through it? Is the future open, or is it already written in the equations of physics? These questions may not have definitive answers, or the answers may depend on the level of description, classical versus quantum, microscopic versus macroscopic, physical versus experiential. Time is both the most familiar aspect of existence and one of the deepest mysteries, a concept that bridges physics, biology, psychology, and philosophy, and that continues to challenge our understanding of reality. Every decision you make unfolds in time. The deliberation, the choice, the action, the consequence, all occur in sequence. This temporal structure is so fundamental to human experience that it shapes language, thought, and culture. We speak of the past as behind us and the future as ahead. We plan, anticipate, regret, and remember. The sense that time passes and that we move through it, making choices that shape what comes next, is central to the feeling of being a conscious agent. Yet determinism, the idea that the future is entirely fixed by the past and the laws of physics, challenges this intuition. If the state of the universe at one moment determines its state at all future moments, then every event, including every thought and action, is the inevitable result of prior causes stretching back to the Big Bang. Free will, in this view, might be an illusion, a subjective sensation with no basis in the underlying mechanics of the universe. Classical mechanics is deterministic. Given the positions and velocities of all particles at one time, and knowing the forces acting on them, you can in principle calculate their positions and velocities at any future time. This determinism was made explicit by Pierre-Simon Laplace, who imagined an intelligence that could know the precise state of every particle in the universe and compute its entire future and past. Such an intelligence, Laplace argued, would find nothing uncertain. The future would be as determined as the past. But determinism does not necessarily eliminate free will. Compatibilism, a philosophical position, holds that free will is compatible with determinism. What matters for free will, in this view, is not whether your actions are determined, but whether they arise from your own desires, beliefs, and reasoning processes. You are free if you act according to your own motivations, even if those motivations are themselves the products of prior causes. Coercion, compulsion, or external constraint would undermine freedom, but determinism alone does not. Quantum mechanics introduces fundamental indeterminacy. The outcome of a quantum measurement is probabilistic. Given the same initial conditions, different results are possible, with probabilities determined by the wave function. This indeterminacy is not due to ignorance. It is built into the theory. Whether this indeterminacy rescues free will is debatable. Random quantum events in neurons might introduce unpredictability, but randomness is not the same as freedom. A decision influenced by random quantum fluctuations is not clearly more free than one determined by prior causes. Some interpretations of quantum mechanics, such as the many-worlds interpretation, restore a kind of determinism. The wave function evolves deterministically, and all possible outcomes occur, each in a separate branch of reality. From the perspective of the universal wave function, there is no randomness, only branching. But within any given branch, the outcome appears random, and observers perceive themselves as making choices without knowing which branch they will end up in. The experience of making a decision feels deliberate and reasoned, but neuroscience reveals that much of what drives behavior occurs unconsciously. Brain activity associated with the decision can be detected several hundred milliseconds before the person becomes consciously aware of making the choice. This has led some to argue that consciousness does not initiate actions, but rather provides a post hoc narrative, rationalizing decisions made by unconscious processes. If true, this would further complicate notions of free will and moral responsibility. However, the interpretation of these experiments is contentious. The brain activity detected before conscious awareness may reflect preparation or bias rather than a final decision. Conscious deliberation might still play a role in shaping the probabilities or vetting the options generated unconsciously. The relationship between consciousness and decision-making is complex, and reducing it to a simple sequence, unconscious decision followed by conscious awareness, may oversimplify the dynamics. Moral responsibility, in many legal and ethical systems, assumes that individuals have the capacity to choose their actions and should be held accountable for them. If determinism or neuroscience undermines this assumption, the implications are profound. Some argue for a shift away from retributive justice toward a model focused on rehabilitation and prevention, recognizing that behavior is shaped by factors, genetics, environment, brain chemistry, largely beyond individual control. Others maintain that even in a deterministic universe, holding people accountable serves a social function, shaping future behavior through incentives and consequences. The temporal structure of decision-making also involves planning and prediction. The prefrontal cortex, a brain region involved in executive function, allows humans to simulate future scenarios, weigh potential outcomes, and select actions based on anticipated consequences. This future-oriented thinking is a hallmark of human cognition, enabling long-term goals, delayed gratification, and complex social coordination. It depends on the ability to represent time mentally, to imagine states that do not yet exist, and to reason about causal chains extending into the future. Regret and anticipation are emotional responses tied to time. Regret arises from comparing the actual past with a counterfactual past. What might have been if a different choice had been made? Anticipation involves imagining possible futures and feeling emotions related to those scenarios. Both require a mental time travel, a capacity to disengage from the present and project oneself into other temporal contexts. This ability is deeply human and appears limited or absent in most other species. Animals, however, do exhibit some forms of future-oriented behavior. Squirrels cache food for winter. Birds migrate in anticipation of seasonal changes. Primates can plan sequences of actions to achieve a goal. Whether these behaviors involve genuine mental representation of the future or are driven by instinct and learned associations is difficult to determine. Humans uniquely can articulate their plans, discuss hypothetical futures, and engage in abstract reasoning about time. The subjective experience of time is also shaped by narrative. Humans understand their lives as stories, with beginnings, middles, and ends, with causes and effects, with character development and turning points. This narrative structure imposes coherence on the flux of experience, creating a sense of continuity and identity over time. Memory is reconstructive, shaped by the stories we tell ourselves, and those stories influence how we interpret the present and envision the future. Culture influences temporal orientation. Some cultures emphasize the past, valuing tradition and ancestry. Others focus on the future, prioritizing progress and innovation. Still others emphasize the present, encouraging mindfulness and immediate experience. These differences reflect varying social structures, economic conditions, and philosophical traditions, but they all operate within the constraints of biology. The same brain mechanisms, the same circadian rhythms, the same memory systems. Technology has altered humanity's relationship with time. Clocks and schedules impose external structure, coordinating activities across individuals and communities. Transportation and communication technologies compress distances, making interactions that once took days or weeks now instantaneous. The pace of modern life has accelerated, with constant connectivity and the expectation of immediate responses. This acceleration may contribute to stress and a sense of time scarcity, a feeling that there is never enough time to accomplish everything. Yet there is no evidence that time itself is speeding up, only that the density of events and information has increased. The same 24 hours exist each day as ever, but they are filled more densely, and the demands on attention are greater. This can create a disconnect between objective and subjective time, where minutes measured by a clock feel different depending on how they are spent. Mindfulness practices, derived from contemplative traditions, emphasize present moment awareness, attempting to slow the subjective experience of time by reducing the tendency to ruminate about the past or worry about the future. Research suggests that such practices can improve well-being, reduce stress, and enhance attention. They work in part by changing the relationship with time, cultivating an acceptance of the present rather than a constant striving toward future goals or escape from current discomfort. The human relationship with time is paradoxical. We are temporal beings, embedded in processes that unfold over time, yet we possess the capacity to reflect on time, to question its nature, to manipulate our experience of it. We are both subject to time's passage and through memory and imagination, capable of transcending the present moment. This duality is part of what makes human consciousness distinctive and what makes time such a rich subject for inquiry. There is a photograph taken in 1990 by the Voyager 1 spacecraft from a distance of 6 billion kilometers that shows Earth as a pale blue dot suspended in a beam of scattered sunlight. The image is humbling. Our planet, with all its history, its civilizations, its conflicts and achievements, appears as a barely visible speck in the vastness of space. Carl Sagan, reflecting on this image, noted that everyone you have ever heard of, every human being who ever lived out their lives on that mote of dust. This perspective reveals something about time as well. The span of human history, the rise and fall of empires, the development of agriculture, writing, science, occupies only the last 10,000 years, a fraction of a percent of Earth's history. Anatomically, modern humans have existed for about 300,000 years. Our genus, Homo, for nearly 3 million years. Life on Earth has persisted for nearly 4 billion years. The universe itself is 13.8 billion years old. The entire story of humanity is a brief flicker in cosmic time. Yet within that flicker, we have learned an astonishing amount. We have deciphered the composition of stars, traced the history of the universe back to its first moments, understood the mechanisms of heredity and evolution, split the atom, and begun to explore other worlds. We have built technologies that extend our senses across vast distances and timescales, from telescopes peering billions of light years into space to particle accelerators probing events lasting fractions of a second. Time is central to this understanding. Astronomy is a form of time travel. Looking at distant objects is looking into the past, because light takes time to reach us. The sun we see is about 8 minutes old. The light left its surface 8 minutes ago. The nearest star, Proxima Centauri, appears as it was 4.2 years ago. The Andromeda Galaxy, visible to the naked eye on a clear night, shows itself as it was 2.5 million years ago. The most distant galaxies observed by telescopes appear as they were more than 13 billion years ago, when the universe was young and stars were just beginning to form. Geology, too, is a study of time. Rock layers record the history of Earth's surface, each stratum a chapter in a long narrative. Fossils embedded in these layers reveal the organisms that lived and died millions of years ago, their forms preserved in stone. Radiometric dating, which measures the decay of radioactive isotopes, provides absolute ages for rocks and fossils, allowing geologists to construct a timeline of Earth's history with remarkable precision. The concept of deep time, the realization that Earth is billions of years old, was not widely accepted until the 19th century. Before then, many believed the Earth to be only a few thousand years old based on religious texts. The recognition that geological processes, erosion, sedimentation, volcanic activity, operate slowly over immense timescales revolutionized geology and biology, providing the temporal framework necessary for Darwin's theory of evolution by natural selection. Evolution requires time, enormous stretches of it, for random mutations and natural selection to produce the diversity of life we see today. The fossil record documents this process, showing gradual changes in species over millions of years, punctuated by periods of rapid diversification and mass extinctions. The molecular clock, based on the rate at which genetic mutations accumulate, provides an independent method for estimating the time since different lineages diverged, and these estimates generally agree with the fossil record. Human perception of time is dwarfed by geological and cosmic scales. A human lifetime is less than a century. While mountains rise and erode over millions of years, continents drift over tens of millions, and stars shine for billions. This disparity makes it difficult to grasp the true age of the Earth or the universe. Analogies help. If the history of Earth were compressed into a single year, humans would appear only in the last few minutes before midnight on December 31st. If the history of the universe were a 24-hour day, Earth would form in the late afternoon, and human civilization would occupy the last fraction of the final second. The future, too, extends far beyond human timescales. The sun will continue to shine for another 5 billion years before exhausting its hydrogen fuel and expanding into a red giant, eventually engulfing the inner planets. Long before then, increasing solar luminosity will render Earth uninhabitable, boiling away the oceans in perhaps 1 billion years. Life on Earth, unless it finds a way to leave, has a finite future measured in hundreds of millions to 1 billion years. The universe as a whole will continue expanding, and current evidence suggests this expansion will accelerate indefinitely, driven by dark energy. Stars will continue to form for trillions of years, but eventually the supply of hydrogen gas will be exhausted. Existing stars will burn out, and no new ones will form. The universe will grow dark, filled with the remnants of dead stars, white dwarfs, neutron stars, black holes, and the cold gas and dust that once formed galaxies. Over unimaginable timescales, 10 to the power of 100 years or more, even black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, where no gradients exist, no energy flows, and no complex structures can form. This heat death, or big freeze, is the ultimate fate predicted by our current understanding of cosmology, assuming dark energy remains constant. Alternative scenarios such as a big rip, in which dark energy increases and tears apart galaxies, stars, planets, and eventually atoms, or a big crunch, in which expansion reverses and the universe collapses, are also possible but seem less likely given present observations. These distant futures are speculative, dependent on physics we do not yet fully understand, but they illustrate the temporal scales on which the universe operates, scales that render human concerns and timescales almost negligible. Yet this does not diminish the significance of the present. The fact that we are here now, capable of understanding even a fraction of the universe's story, is itself remarkable. Time, in the end, is what allows for change, for evolution, for complexity to arise from simplicity. Without time, there would be no stars, no planets, no life, no thought. Time is not merely a backdrop, but an active participant in the unfolding of the cosmos. It is the dimension along which entropy increases, along which the universe expands, along which causes led to effects. Our experience of time, the sensation of its flow, the division into past, present, and future, may be a localized phenomenon, an artifact of consciousness and memory, but it is grounded in the physical processes of the universe. We are not separate from time, we are expressions of it, patterns in the flow of energy and information, transient structures maintaining themselves far from equilibrium as the universe evolves toward disorder. Understanding time, to the extent that we can, does not answer every question. It does not tell us why the universe has the particular laws it does, why time has the direction it does, or whether there are aspects of reality beyond time. But it does provide a framework, a way of thinking about existence that is both humbling and empowering. Humbling, because it reveals our smallness in the grand scheme. Empowering, because it shows that we, as conscious beings, are part of the universe's capacity to know itself. The atoms in your body were forged in stars scattered by supernovae and reassembled here on Earth. The neurons in your brain evolved over hundreds of millions of years, shaped by natural selection. The thoughts you think, the memories you hold, the decisions you make, all unfold in time, part of the great river of causality that flows from the Big Bang to the present and onward into an uncertain future. Time is the shape of change. It is the structure within which events occur, the dimension along which stories are told, the framework that allows for becoming, not just being. To live in time is to be part of a process, to participate in the ongoing transformation of the universe from one state to another. And though we are finite, brief, and fragile, we are also witnesses, conscious participants in a cosmos that has, through us, begun to understand itself. In the quiet of the night, when the stars are visible and the distractions of daily life recede, there is an opportunity to reflect on this, to consider not just the hours and days that structure our lives, but the deep time that stretches behind and ahead. To recognize that the same laws that govern the orbits of planets and the decay of atoms also govern the beating of your heart and the passage of thoughts through your mind. To feel, perhaps, a sense of connection to the vast, ancient, and ongoing story of which we are a part. Time moves forward as far as we can tell, and we move with it. We cannot stop it, reverse it, or escape it. But we can understand it, at least partially, and in that understanding find a deeper appreciation for the fleeting, precious nature of existence. Every moment is unique, never to be repeated, a point in the unfolding of the universe that will never come again. This is not a cause for despair, but for attention, for presence, for the recognition that to be here now, in this moment, is a rare and remarkable thing. The shape of time, then, is the shape of the universe itself, expanding, evolving, exploring the space of possibilities opened by the laws of physics and the initial conditions set at the beginning. We are part of that exploration, conscious nodes in a vast network of causation, experiencing time from the inside, aware of our own awareness, asking questions that may never have final answers but are worth asking nonetheless. And in that questioning, in that search for understanding, we honour the gift of consciousness and the brief interval of time in which we find ourselves alive.